We're going to take a look at L'Hopital's rule today, which is a method that allows us to evaluate some limits that we might not have been able to evaluate otherwise. Just a little background on Guillaume de L'Hopital. This method was actually developed by his teacher, Bernoulli, but L'Hopital is the one that went ahead and published the first calculus book, so he took the credit for this one. Here's Bernoulli. Okay, so let's take a look at the limit as x goes to 2 of x squared minus 4 over x minus 2. If we plugged in 2, we would get 0 over 0, so we don't actually know what that thing approaches. We call this an indeterminate form when we plug in the number and we get an expression that's meaningless to us. We have to then go ahead and try something else to figure out what this thing might approach. One method we've learned for evaluating these is to factor. Cancel the factors, and now we can see that this limit approaches 4. But there are many expressions that don't factor where this method won't work. We need some other way to deal with that. Okay, so if we look at this as a fraction of two functions, we've got f of x over g of x. So f of x would be x squared minus 4, and g of x would be x minus 2. So this limit is the ratio of the numerator over the denominator, or f of x over g of x, as x approaches 2. So here are these two functions, and let's zoom in real close. All right, so we've zoomed in here. We have the red line there is x minus 2, blue is x squared minus 4. And we have the ratio of f of x over g of x. Well, as x approaches 2, this is a really small change in f and a really small change in g. So we have df over dg, or df dx over dg dx. So if we go ahead and take the derivative of f and the derivative of g, we get 2x over 1. Now we can plug in 2, and we get 4. So this is the same thing we got from the other method. Turns out this method will work anytime you have an indeterminate form. So L'Hopital's rule says if the limit as x goes to a of f equals the limit as x goes to a of g equals 0, then the limit as x goes to a of f of x over g of x is the limit as x goes to a over f prime over g prime. So we take the derivative of the top, we take the derivative of the bottom, and then we can evaluate. But it's really important to understand that that only works if the limit of the top and the limit of the bottom are both approaching 0. We're going to go ahead and see how we can confirm L'Hopital's another way. This is not something that you'll need to ever recreate, but it's something that's nice to have seen. And the way we're going to see this is by working backwards. So starting with f prime over g prime, writing out the definition of derivative for each of those, and taking that limit to the outside, because if we're taking the limit of the top and the bottom, that's the same as the limit of the entire thing, which allows us to cancel x minus a and x minus a. Well, in order to apply L'Hopital's rule, we've stated that the two functions need to be approaching 0, so limit as x goes to a of f of a equals 0, and the limit as x goes to a of g of a equals 0. And we're left with the limit as x goes to a of f of x over g of x. And we could take this whole thing and turn it around, starting from the end and working back to the start, and we can see that we have L'Hopital's rule. But notice the key for this to work was we had to have that the limit as x goes to a of f and the limit as x goes to a of g are equal to 0. Otherwise, this proof wouldn't work. Okay, so let's give this a try. Step 1 is to confirm that L'Hopital's rule applies. So we take the limit as x goes to 0 of the top, that equals 0. Limit as x goes to 0 of the bottom, that equals 0. So we know that L'Hopital's rule is going to work. And now I know that this might seem like a lot of extra work, a lot more than we would want to write, but this is a step that I need you to show every single time we apply a L'Hopital's rule problem. It's one of those things that's kind of cumbersome, and it's really because of the way the AP test is structured. On a free response question, if you don't write out each of these limits individually, you will not get credit for the problem. So we need to make sure that we specify the limit of the top is 0, limit of the bottom is 0. Now we can apply L'Hopital's rule. So we have our original limit. Using L'Hopital's rule, I like to put a little h over the equal sign, and we take the derivative of the top, take the derivative of the bottom, and now check again. If we plug in 0, sine of 0 is 0. 1 plus 2 times 0 is 1, so L'Hopital's rule is not going to apply, and we can go ahead and evaluate. We get 0. So you have to make sure that you're checking after you apply L'Hopital's rule, see if we're able to evaluate. If you are, great. If not, we can go and use L'Hopital's rule as many times as necessary. Here's what would happen if you tried to continue with L'Hopital's rule. We would take the derivative of top and bottom, plug in 0, you'd get 1/2. So you can see that if we go too far, we end up getting something completely different. So make sure you stop and check before trying to move on again. Okay, we'll take a look at an example where we can apply L'Hopital's rule more than once. So first, we're going to go ahead and rewrite this. So instead of square root, we have power of 1/2. Let's check the limit of the top, check the limit of the bottom. Those are both 0. So we take the derivative of each. Check the limit of the top, check the limit of the bottom. They're both 0. So we're going to apply L'Hopital's rule another time. Take the derivative of top and bottom. Now when we plug in 0, we end up with negative 1/4 over 2, which is negative 1/8. Okay, L'Hopital's rule can be used for more than just 0 over 0. It can be used for infinity over infinity in the exact same way. So if both limits approach infinity, we can take the derivative of the top over the derivative of the bottom. And there's some other indeterminate forms we have here, which we'll talk about in the next lesson.